Okay, so our next method in bracketing methods is false position method. Okay, now just assume that we have a continuous function again, as you see in the figure on the right hand side. Now the point is this. Remember that in the bracketing method we just calculate the mean value of the XL, the lower bound, and XU and upper bound, and we calculate the mean of this position. Okay, and then we evaluate the function there, and whether we check whether the root is between the new point and upper bound or new point and lower bound, and we continue with that interval. Now here in the false position we do something different. What we do is we draw basically a straight line, okay, and we find the position XR which crosses the x-axis in this case. Now of course at this point this is our approximation, so this straight line is basically an approximation of the function within the interval, a linear approximation of the function, and indeed it is highly probable that the value at XR is not 0. So this is our point. Okay, then what we do is very simple. We now check again which interval to take, identical to the bisection method. Then we draw in another straight line, because we check whether the root is between XR and XL or XR and XU. The only way is we multiply this one XR with the FXU. If it is positive, this means that we need to take the upper interval. Okay, if it is negative, we need to take the lower interval. In this case we need to take the upper interval, and we just, sorry for that, but throw in another line, a straight line for example, and then we check the point that it crosses the 0, and then we evaluate the function again, and we make another approximation at this point. So always, because the root has to lie between the upper and lower bounds, how we calculate this approximation? So basically it gives us the straight line f of xl, xr minus xl has to be equal to f of xu divided by xr minus xu. So from the similarity, of course, this is what we can say easily, and then from here we can calculate the xr, and we evaluate the new value for xr. Of course we can write it in another form like this. So this is how we continuously evaluate the value of the xr, because we want to find the xr. So let's look at the convergence of the false position method. As you see, the bisection method does not converge linearly. It's a little bit oscillatory, and the error is a little bit high compared to the false position, and the false position converges linearly and faster compared to the bisection method. Now let's look at the convergence of the bisection method for a function like this, x to the power 10 minus 1. Of course, as usual, all methods may have some drawbacks, and certainly false position method has a drawback. Let's check the convergence. As you see, after the 5th iteration in bisection method, the error decreases to 4% in bisection method within the interval of x is equal to 0 and x is equal to 1.3 for the function f of x equal to x 10 to the power 10 minus 1. Now, in case of a false position method, as you see, after the 5th iteration, the error is 17.1. Again, it begins from 48, and the bisection methods begin from 100, but doesn't matter. So the point is, the error is much higher in false position method. So why it happens? Now, if we plot the function within the interval that we are looking for, as you see, we constantly draw a line between the lower bound and upper bound, but the point is, the function that we are interested in, or the function that we want to find the root of, has almost a flat bottom. So basically, the derivative of it is almost close to 0 for a wide range of values, beginning from 0 to 0.6, we can say. And as a result, as you see, these are the points where the linear line crosses the x-axis. So we first go to this point, then it comes this here, and then here. So you see the dashed lines. So let's erase the lines that we want. So we begin from 0, so you course here, and then it comes like this, and then goes like this, and then so. So as you see, the steps are quite small. Because of the bounds, in fact. So as a result, it converts very slowly. Our next bracketing method is the false position method. So remember what the false position method is. We basically draw a straight line which connects the lower bound and upper bound, and we find the position where it crosses the x-axis. Certainly you can use different approaches. You can use analytical geometry, you can use the similarity of these triangles, and you arrive at this expression. XR is equal to XU minus some expression. So that's we have seen how we arrive at. So basically you rearrange this equation and you reach to this value, and of course you can do it in a different way. So another approach is, another expression that we can use is this. These two expressions are identical. Now we have seen we have wrote the script for the bisection method for a function in order to obtain the root of a function. But here this script has one defect. So this one. Now certainly this script has a defect, and in fact, as you see, we have if conditions inside the loop. Now conditional statements are computationally expensive, and generally we prefer not to put any conditional statement inside a loop. Therefore we need another condition or another thing to cancel the iteration. And now let's modify the bisection script for the bisection method for the false position. First I will save it with a different name. So I write here false position. Okay, and I changed the name of the function to false position as well. I will modify it because in any case I will just okay, let them stay here. Now remember that while I check the explanation help on for command, I see something there. Break and if return switch continue. Well, it's not here. Maybe I should check the view. I need to find the help menu. Oh, it's okay, it's here. Now on the right hand side you see I have help. I open the help menu now. Now in the search I have the while. I have another command in MATLAB which is while. This is from Simulink, so this is not the link that I need. Perhaps this one. Okay, so here how the command works. I have the while command, I put the expression here, and then the statement. So do this. Here a simple example here, n is 10, f is equal to n. So while n is bigger than 1, do this operation, n is equal to n minus 1, f is equal to f multiplied by n, and so on. So let's see. Is there any other thing? Let's see whether there are any other examples. No. Okay. Let's close it for a while because I need it for a while. So let's change the for loop with while and say that EA is smaller than ES. Sorry, it has to be EA. So remember that EA was the approximate relative error, relative percentage error, and if it is greater than ES, the error bound, it will execute it. It will execute all these things now. Now I delete these lines. So this is my first modification. Now I eliminate one if conditional statement and I replace it with the while comment. Now remember that I'm dealing with the false position and XR has to be modified here. So XL plus XU divided by 2 has to be replaced with either of these expressions. So let's have a look. It is, I will use this one. So XU minus f of XU XU minus f of XU multiplied by XL minus XU and it is divided by again, let me have a look once more, FL minus FU. So this is my next new XR. Okay. Now I can calculate the here the relative error. So for the initial one it is EA XR minus XR previous. We already defined the initial XR previous here. Now certainly in case of a bracketing method we will choose the either side again. If fxl multiplied by fxr is positive, so xr has to be the lower bound. If fxl multiplied by the f of xr is negative, then xr will be the fxu. Okay. So in order to minimize the function evaluations, okay, now I don't need to make any changes anymore. So this is, so let's go step by step again on the script. Now I have the error index. Well, I haven't defined the index. I need an index, of course. So now I put in another line here. Index is equal to 0, and here index is equal to index plus 1. Now, of course, if fxl multiplied by fxr, f of r, then it's negative. Then fu is my function f of xu. Certainly, this means that this is fr. Okay, I'm improving, and I will try to decrease the CPU time now, because I already evaluate this function. So remember that xr is equal to xu, and I already evaluate the function here. So I will replace this line with fr. I don't need to call the function, because calling a function is also computationally expensive. Okay, and fl will be again fr here, because I need to make these tests. else, I mean if test is 0, so this means that one of the values FL and FU is 0, and that is what we are looking for. And of course then we say that XR previous is equal to XR. Okay, now we haven't put any criteria on the iteration max, but let's run the script first and let's check whether it's okay or not. And we reach to the root. Yes, change the folder. Ah, well, EA is unrecognized, so we have to define an EA. We have forgotten to define the EA, so let's define the EA here, and let's say that it is 1. As soon as it's greater than our error bound, it's okay, no problem about that. Now here is my value for the root, beginning from the initial value. Here is my initial value, as you see, and it converts to the actual value within 5 iterations, as you see. So this value is 1. Now here yes, sorry, let's check. This version is a little bit difficult for me to play with it. Okay, here in the 8th iteration it is 14.8037, and it goes like this, so it decreases down to the actual value 8 or 11, so 8011 and so on, and it terminates the iterations in 14. So in 14 iteration it reaches to the actual value. That's okay. And now let me close this figure. This is my figure 2. I have another figure. Okay, now here is my error in percentage. You see in the second iteration it decreases to 8%, and in the fourth iteration I have 1.27%, and in the 10th iteration it is less than much smaller than 1%, even 0.1%. Anyway, so this is how the relative absolute relative error decreases. This is the relative approximate error, by the way. Let's change the, this is relative approximate percentage error. And this is the error. Okay, now my script is finally done, but now I have only condition on the error, but certainly it may take lots of time for me to reach this value, and in fact in many cases I put an additional constraint on the iteration. As we have done here, it was iter max, right? Now how can I do that? Let's go to the help menu again. Okay, now here we have the logical operators, or let's look at the if condition. That's better maybe, because I need another condition. If I need an OR condition. Okay, here operators and elementary, maybe I can find it under this topic. Well, I need a logical operation. That's fine. Here, okay, we have the logical AND, logical NOT, logical OR. So this is what we need. We generally use AND and this condition. So I will modify it. I will put this into the parentheses, and I say OR. I'm looking for the OR in my keyboard, but let's do it like this. First, as soon as index is smaller than iter max, and this has to be OR between them. Okay, I couldn't see it in my keyboard, so let's check whether there is an alternative way of doing it, and I will click on this OR. So yes, this one. There is an alternative way, OR AB. AB performs a logical OR arrays AB returns the containing elements. So let's see the examples. We have an A here, there is a B array, A or B, true, false, compatibility conditions, and so on. So I can use OR command. Okay, so let's check it whether OR will work or not. So I put a comma here and I write here OR. Again, I will check the help menu whether I did it correctly or not. Find logical OR. Okay, it seems okay. So generally this straight line is used, but I couldn't see it on my keyboard. Let me check again. Probably I'm missing. Tilde is here, pointer is there. Okay. Now I found it. But let's run it with this and let's check whether it will work or not. So this is OR. It works. Let's do an alternative way, because I find, and it's written in the help menu, that it may cause some problems in some classes. So it is yes. Here it is. So this is my false position script now. So I just modify my B section. Oh well, this is false position, by the way. I will rename the file. And okay, so as soon as the maximum iteration or index is not bigger than itermax, or EA is bigger than ES, it will do these operations. And either, I mean, both conditions has to be satisfied in this case, and we can use AND command here. So basically this means that it will run until itermax. Oh well, we have to put AND here, no? That's also okay, so it doesn't matter. Logical AND is here, so let's change the OR with the AND. So where is my AND then? It's here. Okay, if this condition is satisfied and this condition is satisfied, then basically we have 1, right? So this is 1, this is true, and this is true. If both sides are true, this condition is true, and then it will run this block. If either of the conditions are false, this one or this one, the condition will not be satisfied and the iteration will be cancelled. Yes. Okay. So it was the same with the previous iteration. Now, as you see, it reached to a certain bound, certain value in the 14th iteration, and it cancels the value there. It cancels the block, running the block there. So this is the logical AND, and you can use such kind of logical expressions in the if condition, because both while and if are conditional statements. Okay, so this is how it works.